Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In the last session, we understood the open loop configuration of an op-amp. And in this session, we'll discuss some of the applications of an op-amp. The very first application we'll be learning is an inverting amplifier. So let us understand how an op-amp can be used as an inverting amplifier. And for the same, circuit is shown here. So here we can see the input signal source is represented as Vin, which is applied to the inverting terminal V2 through an input resistance R1. And the non-inverting terminal V1 has been connected to ground. And I1 is the current that is flowing through the input element R1, and this I1 cannot flow into the op-amp because of the high input impedance what the op-amp offers. We know that typically any op-amp will be having input resistance in mega ohms range, so this current cannot get into the op-amp. So this current will be flowing through the feedback path where we have the feedback element RF. Resistance RF is used as feedback element. So this current that flows through this feedback path shall be called as IF. So essentially this I1 is equal to IF. Now let us derive the expression for the output voltage of this inverting amplifier. So because of the KCL, we can say I1 is equal to IF. That is, the current that is flowing through the input element is same as the current that is flowing through the feedback element. Let us call this as equation 1. And I1, using Ohm's law, it can be written as Vin minus V2 divided by R1. So I1 is written as Vin minus V2 divided by R1, and here we have V2 which is virtually connected to V1 and V1 is connected to ground. So we can say V2 is approximately equal to V1, which is equal to 0. So I1 would be equal to Vin minus 0 divided by R1, which is Vin by R1. Let us call this as equation 2. And now let us derive the equation for IF. IF is the current that is flowing through the feedback path RF. Let us apply Ohm's law here too, so that IF is given by what? V2 minus V0 divided by RF, right? So let us write IF is equal to V2 minus V0 divided by RF. Again, what do we have? V2 is approximately equal to Vin, which is equal to 0. So IF can be written as minus V0 divided by RF. Let this be equation 3. So now we have the expressions for I1 and IF, and let us substitute these two in equation 1. So 2 and 3, let us substitute this into equation 1, so that we can write Vin divided by R1 is equal to minus V0 divided by RF, and V0 will be given by minus RF by R1 into Vin. So this is the expression for output voltage. And the same thing can also be written as V0 is equal to minus A into Vin, where A represents the closed loop voltage gain which is given by Rf by R1. So by varying the values of the feedback element and the input element, we can achieve whatever the gain we want. So here there is a negative sign in the output equation which represents the output voltage will be 180° out of phase with respect to input. So if we draw the waveforms, let us say this is the input voltage signal that has been applied, and this is on time scale. So let us draw the output waveform. So output waveform should be looking like this. So here what we can see is when the input signal has got positive cycle, output will be having negative cycle. When input has got negative cycle, output will be having positive cycle. So this is going to be repeated. So even this is also on the time scale. So what we can see here in the output waveform is, or in these waveforms is, the output is 180° out of phase with amplified level, right? So that is given by the ratio Rf by R1. So this is the working of the inverting amplifier. Now let us understand the working of non-inverting amplifier. As we can see here in the circuit diagram, the input signal Vin is applied to the non-inverting input terminal V1 and the inverting terminal V2 has been grounded. The current I1 is flowing through R1 and this cannot get into op-amp because of the high input impedance. So this current I1 will be flowing through the feedback element Rf as If. So I1 is equal to If. So let us equate I1 to If and consider this as equation 1, and by using Ohm's law we can write the equations for currents I1 and If, and later we'll equate these two. Now I1 is given by 0 minus V2, 0 minus V2 by R1, 0 minus V2 by R1. Because of the virtual connection concept, V2 is approximately equal to V1, which is equal to Vin. V2 is approximately equal to V1, which is equal to Vin. So I1 can be written as minus Vin divided by R1. And let us consider this as equation 2. Now again applying Ohm's law for this path, we will consider the value for If. So If is given by V2 minus V0 divided by Rf, V2 minus V0 divided by Rf. Again we have the value for V2 as Vin from this equation. So If can be written as Vin minus V0 divided by Rf. So let us consider this as equation 3. Now let us substitute equation 2 and equation 3 in equation 1. That is minus Vin by R1 equals to Vin minus V0 divided by Rf. So with this we will find out the equation for V0. So this can be written as minus Rf, sending this to the numerator, minus Rf by R1 into Vin is equal to Vin minus V0, so that V0 is equal to Vin plus, sending this whole term to the other side, so this is what we have. So V0 can be finally written as Vin into 1 plus Rf by R1. So this is the expression for the output voltage of a non-inverting amplifier using op-amp. So this can also be written as V0 is equal to Vin into A, where A represents the closed loop gain and is given by 1 plus Rf by R1. And from this equation, what we can understand is the output voltage will be in phase with the input voltage signal with the gain 1 plus Rf by R1. So the gain can be varied by using the feedback element and the input element Rf and R1 respectively. So the output voltage waveform would look like this. So from this, what we can understand is the output signal is in phase with the input signal with an amplified level. So this is the working of non-inverting amplifier using op-amp. Now we will understand the working of a summing amplifier. This summing amplifier can also be used as scaling amplifier and also as averaging amplifier. Now we have three voltage sources, VA, VB and VC, and these are connected to the inverting terminal V2 through input elements RA, RB and RC respectively. And as we can see here in the circuit, we have current IA that is flowing through RA, IB is the current that is flowing through RB and IC is the current that is flowing through RC. And by Kirchhoff's current law, we can say the current that is coming into the terminal V2 through this input terminal is the algebraic sum of IA, IB and IC. And this total current cannot get into op-amp because of the high input impedance, and this will be flowing through RF as IF. So what we can say is the algebraic sum of IA, IB and IC is equal to IF. So let us get into the derivation of the output voltage equation. So let us say IA plus IB plus IC is equal to IF, and let us call this as equation 1. Now by using Ohm's law, we can say IA is equal to VA minus V2 divided by RA, IB is equal to VB minus V2 divided by RB, and IC is equal to VC minus V2 divided by RC. So IA is equal to VA minus V2 divided by RA IB is equal to VB minus V2 divided by RB, IC is equal to VC minus V2 divided by RC. And we know that V2 is virtually connected to V1 and V1 is connected to ground. So virtually V2 is connected to ground potential. V2 is approximately equal to V1, which is equal to 0. So IA is equal to VA by RA IB is equal to VB by RB and IC is equal to VC by RC. So now we have substitutions for IA, IB and IC, and let us know what is the substitution for IF in this equation. So IF is equal to what? V2 minus V0 divided by RF by Ohm's law. So V2 minus V0 divided by RF, and we know V2 is approximately equal to V1, which is equal to 0. So IF is equal to minus V0 divided by RF. So now what we'll do is we'll substitute the value for IA, IB, IC and IF in equation 1. So equation 1 will become VA by RA plus VB by RB plus VC by RC equals to minus V0 by RF. So now the equation for V0 can be written as, transferring this minus sign to the opposite end and also RF as well, this can be written as minus RF by RA into VA plus RF by RB into VB plus RF by RC into VC. So here we have an expression for V0 which is equal to minus RF by RA into VA plus RF by RB into VB plus RF by RC into VC. Now depending on the values of RF by RA, RF by RB and RF by RC, a portion of VA, VB, VC will be considered for the summation of V0. So with this different values for RA, RB, RC and RF, this circuit can work as scaling amplifier. So this is the expression what we have for scaling amplifier. Now in this equation, if the values what we have for RF, RA, RB, RC, if I consider if RA is equal to RB is equal to RC is equal to R, then V0 can be written as minus RF by R, because RA, RB, RC is equal to R, we can write these values as common out and make this as this. So this is another function what we have for the same circuit. So what we can see here is RF by R into VA plus VB plus VC with the negative sign, and with this equation makes this circuit to work as an averaging amplifier by selecting the appropriate value by making RF by R is equal to 1 by 3. So this circuit works as an averaging amplifier. Now in the same equation, if we equate all the resistance values, let us say if RA is equal to RB is equal to RC is equal to RF equals to R, then V0 will be equal to, here if RF is equal to R, then this cancels, then what we have is minus of VA plus VB plus VC. So here what we can see is this op-amp circuit, if all the resistance values, the input resistance values and the feedback resistance values are equated, then the op-amp will be working as summing amplifier with negative sign. So this is the expression for the summing amplifier. So we have this negative sign in all the equations because the op-amp is connected in inverting mode. So we have the negative sign. So this is the working of an op-amp circuit as an summing amplifier, scaling amplifier and averaging amplifier. So that's all what we have for this session. So in this session we have understood three applications of op-amp. One is inverting, second one is non-inverting, and the third one is summing amplifier, which can also be used as averaging amplifier and scaling amplifier. The difference amplifier or subtractor. As we can see here in the circuit, the difference amplifier has got two inputs, VA and VB. So essentially this circuit would be providing the difference of these two signals. So V0 is expected to be VB minus VA, as VB is connected to non-inverting terminal V1 and VA is connected to inverting terminal V2. Now because we have two input sources connected to two different input terminals, we will be using superposition theorem, which allows us to determine the outputs considering one input at a time. So using this, using superposition theorem, we can write V0 is equal to V0A plus V0B, where V0A is the output considering VA input alone and V0B is the output considering VB input alone. Let us determine the output expressions for V0A and V0B. Considering VA alone, this one, looking at the circuit, if I consider VA alone, VB should be grounded. So the op-amp circuit works as an inverting amplifier. So V0 for an inverting amplifier is given by minus RF by R1 into Vin, whereas V0 is V0A and Vin is VA. Therefore, V0 can be written as V0A can be written as minus RF by R1 into VA. So this is the expression what we have for V0A. Likewise, we'll consider VB alone. Considering VB alone, in this circuit, VA should be grounded when we consider VB alone. Then the circuit will be working as a non-inverting amplifier, where V0 is given by 1 plus RF by R1 into V in, where V naught is V naught B and V in is this terminal V2, which is nothing but V1 because of the virtual short concept. Now, looking at the circuit, V1 can be determined by using voltage divider rule. So, V1 is equal to, here V1 is given by VB into RF divided by R1 plus RF. So, V1, let us put this as VB into RF divided by R1 plus RF, so that V naught B will be equal to 1 plus RF by R1 into RF by R1 plus RF into VB, right. So, this can also be written as V naught B is equal to, by considering this, rewriting this as R1 plus RF divided by R1 into RF by R1 plus RF into VB. Now, these things can be cancelled. Now, what we have is V naught B is equal to RF by R1 into VB. So, now we have the expression for V naught A and also V naught B. Let us substitute these two in this expression. So, let me rewrite this as this, and V naught, now V naught is given by this one minus RF by R1 into VA, and this one plus RF by R1 into VB. So, where V naught can be written as RF by R1 into VB minus VA. So, now if we equate RF and R1 value, then V naught will be equal to VB minus VA. So, what we can see here is, so the output voltage is equal to the difference of the two input voltages VA and VB, because VB is applied to the non-inverting terminal and VA is applied to inverting terminal. The output voltage is given by VB minus VA. So, this is the working of the difference amplifier or subtractor. Now, let us understand the working of the op-amp integrator circuit. Now, this is the circuit diagram what we have for the integrator, and here we can see the input signal Vin is applied to the inverting terminal V2 through input element R1, through which current I1 is flowing, and non-inverting terminal V1 has been grounded, and capacitor C has been used as the feedback element, and the current I1 which is coming through R1 cannot get into the op-amp because of the high input impedance, and this will be flowing through the feedback path charging this capacitance, and we'll call this current as IF. So, I1 is equal to IF. Let us equate these two. I1 equals to IF, and let us put up the values or the equation for I1 and IF. By using Ohm's law, I1 can be written as here Vin minus V2, Vin minus V2 divided by R1, and V2 is approximately equal to V1 because of the virtual short concept, and V1 is equal to 0, so V2 will also be equal to 0. So I1 is equal to V in by R1. So this is the expression what we have for I1. Now coming to the feedback path IF, which is charging this capacitance C. So this can be written as C into d by dt of the potential difference, that is V2 minus V0, and V2 is approximately equal to V1, which is equal to 0. So IF is equal to minus C into d by dt of V0. Now let us equate I1 and IF. So this is going to be V in by R1, which is equal to minus C into d by dt of V0. So now V0 can be written as d by dt of V0 is equal to minus C into this R1 into V in. So now what we have is d by dt of V0, and what we need is V0. So what we'll do is we'll integrate both the sides with respect to time. So what we can put up here is integration d by dt V0 with respect to time is equal to integration of minus C into R1 into V in with respect to time, right? So now here we have the integration and the differentiation. So these things cancels and we are left out with V0. So V0 is given by this C and R1. These two are the constant values. With the negative sign, we'll keep these out of the integration. So minus R1 into C integration of V in with respect to time. So this is the expression for the output voltage of the integrator circuit. So what we have is there is a gain which is given by R1 into C, and negative sign indicates the out of phase signal and the integration of V in with respect to time, and the same thing has been shown in the output waveform with respect to the inputs. So this is the working of integrator circuit. The next circuit we have for the discussion is op-amp differentiator. And this is the circuit diagram for the op-amp differentiator. As we can see here, the input element is capacitor and the feedback element is the resistance. The input signal V in is applied to the inverting terminal V2, whereas the non-inverting terminal V1 has been grounded. And the current I1 is charging the capacitor C, and this I1 cannot enter into the op-amp circuit because of the high input impedance, and this current will be flowing as IF through the feedback path. So I1 is equal to IF. So let us write I1 is equal to IF, and writing the expression for I1 using Ohm's law. So this I1 is charging this capacitor C. So this can be written as C into d by dt of V in minus V2. And we know V2 is virtually connected to V1. So V2 is going to be 0. So I1 is equal to C into d by dt of V in. And let us put up the expression for IF. So IF is given by V2 minus V0 divided by RF. So V2 minus V0 divided by R, and V2 is equal to 0. So IF can be written as minus V0 divided by R. So let us equate these two equations. So minus V0 by R is equal to C into d by dt of Vn. So V0 can be written as V0 is equal to minus R, this R goes here, into C into d by dt of Vn. So this is the expression what we have for V0. So here we can see output voltage V0 is given by differentiation of the input voltage multiplied by the gain factor given by the resistive element and the capacitive element with the negative sign. So again negative sign we have because op-amp is connected in the inverting mode, and this is the input waveform and output waveform for the differential. Next we will understand the operation of op-amp voltage follower. Op-amp voltage follower is also basically a non-inverting amplifier. Let us put up the circuit diagram for this and understand what we will be getting at the output of this circuit. So here this is the op-amp what we have, and this we have the non-inverting terminal V1 and the inverting terminal V2. As I said, the voltage follower, op-amp voltage follower is also basically a non-inverting amplifier circuit. But the difference here what we have is the inverting terminal will have no input element, will make it open circuited, and the feedback element also will take out and make it short circuited. So here this circuit looks like this, and here we will be applying the input signal. So what we have, the input element is open circuited and the feedback element is short circuited in this circuit. And we know for a non-inverting amplifier circuit, output voltage V0 is given by 1 plus Rf by R1 into Vin. This is for non-inverting amplifier. But in this case, as I indicated, the input element has been open circuited and the feedback element has been short circuited. So here Rf will be equal to 0 and R1, the input element, is going to be infinite because of the open circuited condition. So substituting these here, we will be having V0 equals to 1 plus 0 by infinity into Vn, which is nothing but 1 plus 0 into Vn, which is nothing but Vn. So here V0 is going to be same as Vn. So the name given voltage follower, or this can also be called as source follower, because output follows the supply source or the source signal. The circuit is also called as the source follower circuit. So the question may be, if the output is going to be same as input, what is the usage or application of this? Mainly the source follower or the voltage follower will be used as buffers. So buffers are the one which will be used as isolation circuits, and for current amplification purpose these buffers will be using. So this op-amp circuit has got advantages like huge input impedance and almost zero or low output impedance. This circuit or this logic can be used as buffer where voltage need to be maintained same. Here you can see output is equal to input. So voltage is going to be maintained same. So we can say gain is equal to 1. This is also called as unity gain amplifier. So this can be used where we have to maintain the voltage same as the input but enhanced current levels if you want, then we'll be using these buffers. I mean, we can use this voltage follower or source follower as buffer circuits. So these are the applications what we have with respect to op-amps in this course. So in this session we have understood some of the applications of op-amps like the inverting amplifier, non-inverting amplifier, summing amplifier, difference amplifier, integrator circuit, differentiator circuit and the voltage follower circuit. Thank you.